Hello and welcome to the third lecture in ninth chapter of our comprehensive course on data science, machine learning and artificial intelligence. Here we were discussing EDA, exploratory data analysis part 1, and in this we are at present doing univariate analysis, and so far we have progressed that much that some employee came with employee details data set like this, and you did some deduplication and non-imputation, outlier capping, and finally you got one cleaned employee details dataset. Now our aim is to start our univariate analysis on that cleaned employee detail. We saved it in our current working directory. So now we are starting univariate analysis. And in univariate analysis, just a distribution and statistical summary, those two are not enough, but many more things are required. For example, this whole discussion, but we will do this discussion after executing the code so that things will become more clear. So we are loading our cleaned employee detail data frame. Okay, so let us load read_csv and we are loading it. Now we are printing statistical summary, for which numerical summary and categorical summary. Now df.describe by default means df.describe include equals either int 64 or maybe whatever, depending upon the architecture of your computer, and then float. So it will include only these two types. That means it will by default include only numeric data types. So there is no need to specify include. But when you want to print a descriptive stat, it will not give descriptive statistic for categorical variables. So if you want to give categorical variables summary, then you have to use include is equal to object. Okay. So for all numerical variables, we know that this is the summary, this, and we get this output. Okay, or let me take this to another cell. That would be better, because one output so lengthy becomes confusing. So now only numerical variables. So you are getting this descriptive statistic. As we know, that means mean, then minimum values, maximum values. So difference between them, that is called range. So you roughly get that range of this is 9,000 something to 1,300, or that is around 8,000. Range of this is 73,000 to 20,000, means around 53,000. Range of this is 49 to 21, means only around 27 something. And range of this is 11 to minimum is 2, so 9 only. So various numerical variables, their scale is pretty different, and that means this much analysis should itself make the person clear that I will have to apply scaling, that is bringing all the variables to same scale. We learned earlier in previous chapters that there are two standard methods of scaling. One is called normalizing and another is called standardizing. In one, we bring all values between 0 to 1, so minimum and maximum values are adjusted to 0 and 1, and in another we bring all values such that their mean is at 0 and their standard deviation is exactly 1. So we will have to do that. That much is clear, because the scales are pretty different and many algorithms don't like this kind of data. So normalization or standardization will be required using sklearn.standard scaler, that we know. Okay. Now categorical variables summary. So each categorical variable summary we are printing one by one. So employee's date of birth. Now that shows that this date of birth is held by 3, this date of birth is held by 1. So that is expected, because only 50 employees are there. So there is a rare chance that many of them will be having same date of birth. Employee's date of joining. This person has 4 date of joining, this has 2 date of joining, these all have 1 date of joining, like that. So that means that it is clear that again the recruitment of all employees are occurring on a mostly different dates. Okay. Now qualification. Then in qualification we see that 18 are master degree holder, 12 are bachelor degree holder, 11 are high school holder, and 11 are PhD. Now employees marital status frequency distribution. So 16 are widowed, 13 are divorced, 12 are married, and 11 are single. Okay, so this is the marital status distribution. And employees department, so finance department has 12 people working, HR has 11 people, IT has 10, sales has 10, and marketing has 10. So this is about the summary of categorical column, for which we use this for loop, that for column in df.select dtypes include equals object dot columns, that means include categorical columns. So this is actually like just that only. For column in categorical columns, print column frequency distribution, and then you write column dot value count. Okay, you can also add one more thing, I think, because describe will work for categorical column also. So print what, then print statistical summary of that column, and what will be that statistical summary? Then that will be column, sorry, describe uh, df column, rather df column dot describe, and include equals object. I think this should work mostly. This initial describe I am removing. This whole thing is variable because for every column this thing will change. So in f string this much part should be put in a variable that is curly braces. Most probably this should work. Okay, yes, it is working, and now you can see not only that value counts are seen, but even statistical summary of each categorical column is also seen. So actually this is better than just value count. So I am just removing that value count line. It is unnecessarily occupying this lot of vertical space and still giving very little information. This is much better because it also gives the value counts. Okay, so for this categorical column, first categorical column, the count is 52, unique are 39 value, top value is this okay, statistical summary of column, so that it is clear which column's statistical summary. So statistical summary of employee date birth. So top employee date birth is this, frequency is 3, and so on. Similarly, employee date of joining, unique values are 4, top value is master, frequency is 18, and so on. So you can get much more detail. You can even keep that value counts also. That also gives some information. Fine. Now visualizing the variable. For visualization, we know that we use SNS library, and we use SNS.histplot, then SNS.boxplot. But apart from that, we want to plot another type of graph also. So bar plots, then SNS.barplot, density plots, pie charts, and missing value. And this time I want to do it in slightly elegant manner. Elegant manner means what? When I execute, I don't want all plot to be plotted here, one below another, because you can imagine there are so many variables, and box plot for each, and box plot for histogram for each, then pie chart for each, and that will create a very lengthy output here. So instead what I am doing is I want to create some directory here, a folder here in my base directory that will save all the plots. Okay, so I am creating base directory, and for which I am importing this OS module. It is a built-in library in Python, so you don't have to do pip install or anything. Import OS, and then os.path.join os.get current working directory. So current working directory means the directory in which this script is executing. So that is this, whatever it is. So this much will get current working directory. C users e cube, and that means it will give this C users e cube basic ds pi 311. You can see that all my chapters are executing in that directory. So that is the meaning of that CWD, and thereafter it will attach employee details with it. So that means this much code will do what? That will first get current working directory, C users e cube basic ds pi 311, and that will put one new folder, create one new folder, employee details inside it. So that is then assign that as my base directory. Then inside that employee details folder, it will create these many subdirectories. And remember, this code will not create those directories. It is just specifying that this is my base directory, this is my subdirectory, and when this for loop is executed, then your directories will be created. So let me take this in a different cell. Then you will realize that, and even these also I am taking in a different cell. Okay. So here, when I execute this, no directory will be created, but I have assigned the value where I want to create directory. Then in my current directory, and the name of that folder should be this. Inside that folder, there should be this many new folders whenever they are created. Now this will create those directories. These numerical columns should come here. Okay, it is consistency with next cell. Okay, so this for loop creates that for subdirectory in subdirectories. That means it will take one from each this list one by one. So for box plot, os.make directory, os.path.join, base directory, subdirectory. So that means base directory is employee details, and inside it subdirectory is whatever first value you have taken, box plot. Exist, okay, true. Then it will take the other one, histograms, and again it will create base directory, employee details, and create the subdirectory, histograms, and again exist, okay, equals true. That means if the directory is already existing, because first time when you execute code, at that time nothing is there at present, but I may need to execute this code again and again while I am refining my machine learning model. So it might be already existing. Then it throws error otherwise, that directory already exists and you have to delete that old directory and all that. So I don't want that trouble. So therefore I have said that exist, okay, equals true. So if it is already existing, fine, just overwrite it. That is the meaning. Okay. So let us now execute this, and you will see that here some directory will come into existence, employee details, and it is currently having 5 folders: box plot, histograms, bar plot, density plot, pie chart, and missing value heat maps. You can see that this is a better way of arranging everything, because later on when I am creating my report for my client, at that time I will have to use this plot, some of this plot in the report to explain that, oh, your data has this many issues still, and please do something that do some modification and create the data. Okay, that will give better data or modified data. Or you may say that your data has these issues, that its distributions are not normal but maybe exponential or logarithmic, or that kind of simplification I will have to do. So you should explain. The client continuously should be kept in loop that you are working on this his problem, and these are the issues which are arising, and due to these issues you are taking these simplifications, and due to that simplifications his final model and its accuracy might be impacted like this. So if he's okay with that, because after you do everything and if the client disapproves the initial step itself, then it would be very difficult for you to do all the steps once again. Instead, better to continuously keep client in loop. So it is an iterative process. That's do some things, inform the client and take his feedback, do some more things, inform the client and take his feedback, like that. Now numeric columns we are separating. So it is from df include int 64 float 64, that many column as selected underscore d types. So that is numeric columns, and then separate them. For all numeric columns we will plot histograms, and we will also plot box plot. So that is these numeric columns, histogram and box plot. So this is the for loop which will plot the I think which plot, yeah, hist plot. So let us currently, if you see this folder histograms, then it is blank. Okay, so let us execute this, and perhaps now the folder will be filled. Yes, histogram of age, histogram of this, and so on. Similarly, this next for loop that will plot box plot, sns.box plot, and currently box plot folder is blank. But now when I execute this for loop, then it will save, and now box plot, if you see, now box plot folder is filled. Density plot, that is that smooth curve. I want to see whether the data distribution is exactly matching with the Gaussian distribution bell curve, or at least if it is not exactly matching, then how far away it is from the ideal Gaussian distribution or bell curve. Because many algorithms, their basic requirement is that data should be normally distributed. So you have to first check that whether a given data on its own is normally distributed or not. If it is not normally distributed, then you can do something so that it is normalized. So this is density plot. Again, this folder is at present empty, but now I can do this. So density plots, this is my density plot, right? Now visualizing categorical variables. So categorical columns are these: df dot select underscore d types, include is equal to object. Just like here, you wrote include is equal to float 64 and int 64. This one. Similarly, here you write include is equal to object. So you are separating categorical variables. Once categorical variables are separated, you can plot two different types: bar chart and pie chart. So first about pie chart, then this for loop takes each categorical variable one by one and uses this thing, sns.count plot. Now this you have to remember that bar word that is not used by Cpon library. It uses a count plot word. Okay, so that is something which you must remember. And similarly in the pie chart also you see that there is no direct code for plotting pie chart. That is instead you first have to do value count for each category, and then you can do plot.py. So these are slightly complicated code, but now you should not bother about this, because I have already taught that these AI tools are there. There are free tools also, and or there are paid tools also if I want to use OpenAI and all that. So you just have to take your categorical variables which you have already separated here, cat columns, and ask a prompt here that I have following categorical variables, and give a list of all categorical columns which you have got here. Give me code for plotting their bar chart using SNS library and their pie chart using SNS library, and it will give you Python code directly just within your Jupyter only. So that means there is no need of doing so much of coding again and again. Okay, and what they do in industry is that once this type of code and columns are written, then they will just keep on using. These are all reusable code. If you see, nowhere any specific data set is mentioned, no. Nowhere any specific column name is mentioned, no. So tomorrow another data set will come. I can just use the same code to plot a bar chart, etc. for that data set. Okay, because nowhere specific column names like employee details or employee salary, etc. are mentioned. So it is just a general script which will plot all the plots. So let us see bar plots first. So in my employee details, currently the bar plot folder is empty. You can see there are no bar plots, but now I execute this and refresh. So bar plots are coming into existence. Similarly, this is pie plot. So currently pie plot has nothing. I execute this and immediately the folder will be populated with pie plot. Refresh and you will see that pie plots are there. So this is one important way in which all plots are saved in a nice centralized manner rather than displaying them in Jupyter Notebook and creating a lengthy and cluttered Jupyter Notebook. And this will be a reusable thing. You can use it while creating dashboard for your client or other things. This also serves as a good proof of work because whatever is in the Jupyter Notebook, when you shut down the kernel at the end of day's work, then that work is gone. But here this work is saved. So you can use that as a proof of your work. If you are working as a data scientist in a firm and your boss asks that what progress have you done, then you can show that. Okay. Now for column in numeric columns, this is for detecting outlier. We have decided that outliers are what? Values which are less than Q1 minus 1.5 times interquartile range and values which are more than Q3 plus 1.5 times interquartile range. These two are outliers. This is the lower bound of outlier and this is the upper bound of outlier. And therefore interquartile range is Q3 minus Q1. Then outliers are DF column less than lower bound. So all values which are less than this value and otherwise or they are values which are greater than upper bound. So all values which are greater than this value. Okay. So that you are finding. But remember here we are just okay, yeah, we are printing the outliers. So fine. And outliers in employee ID. Now in ID column, even if they are there is nothing much in that. Salary, no outliers. Age, no outliers. Performance ranking, no outliers. We are taking only numeric columns. Okay. Now outlier with box plot. Okay. So this way. These box plots are now not saved because we have already saved them. These are just to view outliers. And if outliers are there, then we know that in the box plot they will be clearly shown as a dot dot dot. So here there are no outliers that is visible. So whatever results you got here, same result you are getting here also. Okay. Now distribution shape. Distribution shape is that smooth how much the bell curve is extending over one side or other side. That is a skew and kurtosis. So for that I am using for column in numeric columns. That skew and kurtosis also applies to numeric columns only. Skewness is df column dot skew and kurtosis is df column dot kurtosis. So this will traverse through all numeric columns one by one and find the skew and kurtosis and print them. So employee ID, now there is no point in finding skew and kurtosis in that, it is just ID column. In salary, the skew is 0.10, kurtosis is 0.35. Here skew is 0.14 and kurtosis is 0.94, and here the skew is 0.13 and kurtosis is 0.20. This is exploratory data analysis. So that means we are just detecting that in various and in that also univariate analysis. So we are taking one variable at a time, this or this or this or this, and we are just detecting if there is skew and kurtosis in that variable. Okay, but we are not doing anything with that. Suppose we find that this much kurtosis is not acceptable, then there are ways to handle that thing. Or skew is not acceptable, then you can take some logarithmic transformations and many other things, but that will come later on. So we are just noting down that these are the values of skew and kurtosis, so that whenever later on that data pre-processing stage will come, applying those transformation, feature transformation and feature engineering, all those things, at that time, if required, we will do that feature engineering. But for that, you have to first know whether it is required or not. Okay. Then detecting modality. So modality means many times instead of a single bell curve, it is possible that multimodal curve is coming. Since instead of bell curve, it will be slightly distorted shape, not perfectly bell curve. So you have to take numeric columns one by one. We are taking and we are plotting KDE plot, that is kernel density plot, smoothened plot using SNS library. So this is for employee ID. ID columns distribution is not much important. So fine, but this is for a salary. Now it looks more or less normal. A little bit disturbance is seen here on the higher side, but more or less normally distributed. This is age, again more or less normally distributed with a little bit distribution, and this is what I said by multimodal. One peak is coming and then some trough and then some small peak is coming and then another trough. So multimodal, but it more or less normal. And similarly this employee performance ranking is also more or less normal. If these are far away from ideal bell curve, then we have to do something to bring them similar to the bell curve or normal distribution, provided we are going to use certain algorithms which are sensitive to that. So some algorithm require the data to be having this bell curve shape distribution. So we are again just noting down that this is the distribution for various numeric variables, and I'm finding that it is more or less looking satisfactory. Mostly I will not have to do any conversion. Now missing value count. So we have already done the missing value treatment, so we already know that there is not going to be any missing value count. Okay, but still let us put, and here in employee details there is one library, one folder, missing value heat maps. So you can use it, but nothing will be there in that. Okay, one is coming, but heat map will be blank. So that means blank means uniformly printed. If there are missing value in say any column, like this column or this column or this, then that much will be shown as a white portion. White means missing value. So here somewhere white is there, then that means second row is missing value in salary. Here somewhere white is seen in age, so that means 44th row is missing value in the salary. But everything is colored, so no missing value. And here output in letters also shows that there are zero missing value. We removed missing value. We did our imputation in previous lecture. Now frequency distribution for so that value counts which we have done earlier also. So we are just showing that for each categorical column how many are the values for each category. So in employee date of birth, so many categories are there, and almost each date of birth is unique. Employee date of joining also, so many categories are there, and almost all date of birth are joining are common. Only these 4 fellows were employed hired on same day, and these 2 fellows were hired on same day. Okay. Then department wise, degree wise value count, then master, bachelor, high school, PhD. Then marital status wise value count, widow, divorce, etc. And department wise value count, finance, HR will have how many employees out of total 50 employees. Finally, we are just saving this visualization and rather saving the summary statistic, because visualization have already been saved, but the message we are printing in last step, summary statistic is saved as summary statistic .csv. And what is summary statistic? That is just df.describe. That we have already done much at the beginning. This is summary statistic, right? But there it is displayed just below the Jupyter cell. So as I said, if I shut down my kernel and tomorrow I resume my work, then that information is lost. So if I want to save that as a permanent file, then I am saving it by this command. Okay, that 2_csv. Just like for reading the file, we use read_csv. For saving the file, we use 2_csv and summary statistic.csv. But here this df.describe, its output is not very nice to save it, because this is first categorical column, that is employee date. Then it's this is second categorical column, date of joining. This is third categorical column, qualification. This is fourth categorical column, marital status. This is fifth categorical column, department. So in short, I am getting different columns one below another, but I ideally would like the columns one beside another. So that is better way of saving. So in that last step, what we do is, before saving my statistical summary of this obtained by using describe, I am using one t. That t is for transpose matrix. Transpose matrix. Now we will do some detailed discussion on matrices in statistics. At that time you will see transpose. But transpose is just that if there is a matrix is just a table, then convert its vertical to horizontal and horizontal to vertical. So there, what was our problem in the output of describe? Our problem was that rows were distributed vertically. Here, column names are coming vertically one below another. So that this t will make them horizontal, vertical to horizontal. So first column name, date of birth, then next date of joining, then next qualification, then next marital status, then next employee department. All these will come. Okay, so save, and let us see that saved file. And I will open also summary statistic.csv, and you can see it has come in existence just a few seconds ago. Summary statistic.csv, and you can see nice the column names are here, and all summary statistics, they are in very legible format. So for employee ID column, the summary of count is this much, mean is this much, and very nice to read. Okay, just one t for transpose. Okay, then this is how univariate analysis is done. Now if we continue our data science life cycle, suppose that is a real project which client has assigned to me, then I will now next move to the bivariate analysis. That is chapter maybe not this but exploratory data analysis 1 we have done. 9th, so where is 10th? Okay, 10th, I think I will have to open from here. But then we will do exploratory data analysis 2 further, in which now we will do bivariate analysis, that is study of analysis of part 2, study of two variables at a time. So after univariate, bivariate. So we are still moving in this region actually, first this purple region. And once we understand both univariate and bivariate analysis, then we will try to go to feature engineering. We are moving at present purple and red like that. So that means EDA and visualization, EDA and visualization. So see you in the next chapter. And in this chapter, EDA part 1, I have given some exercises at the end. So try to do, because we have done enough discussion. This is first exercise question, and I have even given how to create the data for it. And this is second exercise question, how to create the data for it. And this is the third exercise question. Data creation I have given so that I can match every learner's answer. Otherwise, I can tell you that you create your own data, and now I know that you are all very brilliant people. You can create your own data, but then everybody will create different column names and different features. Then it is difficult to come to a common answer. So please do these three, and you will get the solutions also after a few days when this particular chapter is over. So today this is over, and we will start with chapter 10 next. Thank you.